Hi, my name is Phil Wagner, and I'm a technical writer working on machine learning education. And in this session of Explore ML, we're going to be talking about problem framing. Before we do that, I want to review some of the facilitator notes because I'm talking to facilitators. And so when you're presenting slides, try using live captions. And so I'm going to turn those on right now. Okay. And then uh, throughout the session, it's okay to say, I don't know. It's okay to say, I need to look that up or let's look that up together. We're not expecting you to be experts. What we would like is for you to be yourself because the goal of this is to inspire and excite. So we want people to come away from this having a really positive experience about machine learning education. So smile and enjoy yourself and share your experiences, any, positive struggles, positive things, struggles that you've had, any kind of thing. It really helps people come away feeling like they had a good session. Be aware of your unconscious bias. If you, for example, tend to um, prefer lecturing, you learn really well from lectures, you're more likely going to present as a lecture. But perhaps other people prefer having a discussion. And so you need to be aware of that and how you can help them with that. You also may think that certain things are easy because of your background. Maybe you have some programming experience or something else, and we want to make sure that people with other experiences and backgrounds are welcome in this environment as well. So be aware of those things, think about them, and account for others. Now, to that point, we want to encourage active learning, which means try and ask for questions as often as possible, encouraging everybody to participate. So, for example, one way we found that getting people to ask questions in a environment like this, where not everyone knows the concepts, and if they're afraid of perhaps looking foolish, is rather than asking if they have any questions, ask what questions they have, and that gives permission and says this is a place where and the topic where you're going to have questions, and it's okay to wait up to 10-15 seconds for people's questions. We want to empower people to solve their problems. We're not the experts. We want to encourage them to find the answers, to explore, to not depend upon us in order to know what to do. And so resist the urge to take the keyboard if it's that kind of thing. But in other situations, maybe if someone asks you a question, turn it back to them and say, what would you do in the situation? Or ask other people in the room. Remember that everyone has different levels of experience with machine learning, computer science, and technology. So not everyone has the same level of background that you do. And so it's okay to slow down. It's okay to ask them questions if I'm going too fast or if they have any questions about words that I'm using. It's okay to define jargon. It's okay to spend a little bit more time with someone who maybe doesn't have a background in programming. And on the other end of the spectrum, if they are advanced and it looks like they're bored or they're finished early, you can talk to them about how they might extend the project scope and how they might do more. But to that point, for the general group, stick to the schedule. Please feel free to swap in a slide if you think that there's something better. Do let us know so that we can improve the slides, but don't add to the lecture the slides very much because that's going to let we've budgeted only so much time for people, and we don't want to end up taking more of their time. We want to be respectful of their time. And if someone comes with a question that's very detailed or abstract or niche to their interest, but maybe it's going to only confuse everybody else, it's important to say things like, that's a great question. Why don't you come up to me afterwards and let's talk about that? Or after everybody's talking amongst themselves, let's talk about that. Finally, in order to convey the best of yourself, make sure that you're doing things like checking your posture. So if you tend to fidget or put your hands in your pockets or look down or mumble, check your posture to make sure you're giving the best presentation you can. Vary your tone, so not monotone, but inflection, asking questions, avoiding filler words. This is my personal pet peeve or my personal struggle, which is I tend to say things like and it's something I have to slow down and think carefully about. Make eye contact with everybody. People came to your session rather than going and watching a video or reading a tutorial. So make sure that they feel connected and welcomed by giving them eye contact as you talk, not in a silly way necessarily, but as you're going through, don't always stare at this one person or one part of the room. And finally, pause and breathe. Enjoy yourself, have fun, catch your breath. If you do this, you'll think more carefully because your brain is able to catch up to your mouth. You're less likely to say like and you won't feel stressed out. You'll be able to have a good time. So let's get started with problem framing. Now, problem framing can be one of the most important parts of machine learning next to your knowing your data, because machine learning systems learn from patterns in data, but you can't measure if your system is doing well unless you have a problem that it's trying to achieve. For example, you could maybe say it has 100% accuracy, but 100% accuracy at doing what? And so you also want to make sure that you have 100% accuracy. Well, I keep using the phrase 100%, but you'll never have 100% with machine learning. But um, you want to make sure that your goal is very well articulated, because the machine learning system is going to try and reach that goal. But if this is your goal and yet your system is trying to train for this slightly different thing, that's going to confuse. That's not end up going to be right for your end users or your consumers. And so framing your problem is something we're going to talk about so that you can know when your model is successful. Now, if this were a live session, I would ask people to tell me what supervised machine learning is, just as a recap. So you can summarize what you know in pairs. So 90 seconds, talk to each other, come up with an answer. But since this is not a live session, I would have those groups then share back with the group. But I will say to you, the facilitators, what's in the speaker notes, which is machine learning systems take input and make useful predictions and decisions based on previously unseen pieces of data. So, in short, taking data, learning from it, finding the examples and the patterns, and then using that to make predictions on new data. Another definition that's popular is computers learning how to do a task without being explicitly programmed how to do so, without having articulated rules by humans. But the point is, what supervised machine learning is using labeled data as an additional source of information. What the difference about that is between unsupervised learning is when we feed this machine learning system, train it on data that is labeled. That means that the photos of cats and dogs are actually labeled as cats and dogs. Whereas another type of machine learning called unsupervised machine learning might learn that cats have these attributes. They're not explicitly told that this is a cat. They're just saying, this is how I would group this photos. These are cats, these are dogs. That's something it would emerge, or it would probably say something like, this is group one and this is group two, because it has no idea what a cat is. Okay, so supervised machine learning. Some other terminology you might not be familiar with are that we'll need in order to talk about problem framing. One of them is a label. So a label is what we're trying to predict. So it's called Y in some literature, but it is the cat or the dog or whatever you're trying to, as you go through it, you're trying to label it. If you're trying to uh, determine if something is high priced or low priced, you might do that. Or if you're trying to label something as the recommended video, that could be it too. Um, Features are something that we talked about in a previous session about neural networks, and that is what you're inputting in, and it describes the data. And so this could be, using the mathematical terminology, we call it x1, x2, and those kinds of things in linear regression. But another way to think about features are how to describe your data. So if you were cats and dogs, you might describe the color of its fur, the length of its tail, the sound of the sound that it makes. Those are all features that you could use to describe it. If you were describing a house, you might describe it as the number of bedrooms it has, or how many square feet it is, or square meters, or how large it is, or where it could be found. Those are all features that you can use to describe the data. Now, an example is in all of your data, one particular piece of the data. So here's your data. This is an example. This is an example. This is an example. It's a specific thing that you're looking at. A labeled example, remember we were talking about supervised machine learning, is when when you give it the input data, but you label the input data. So you say, this is a cat, this is not a cat. So that might be this, you're feeding in this features, whether it's a picture of a cat. We always use cats and dogs, but you could use lots of other things. So this is a cat. It has the tail this long. It is this big. It makes a meow. It is this color. And then you could have another cat that is this color and then makes this kind of meow, and it is this size. You could have a dog that is this size. But again, going back to our other example, it could be this house has 300,000 square. This house costs $300,000, or whatever currency you'd like to use. But this house also has 2,000 square meters. This has this many bedrooms and that kind of thing. So we use those to train the. So I didn't mention that this is used to train the model. An unlabeled example is the new data. You test your new data. So you train the model. You want to make sure that it can do as well on the old data or the training data as it does on the test data, on the new data. And so you might say, here's a house with 3 bedrooms. How much should it cost? And the model would try and predict. Or here is a animal that makes this sound. What is it? The model is, it sounds like a fancy term, but it's basically saying, here's the example, here's my prediction. So if it's this and this and this, then I think it's a cat. If it's this and this and this, I think that house is going to cost this much money. And so that's all a model is. It's a complex mathematical equation that takes data and says, okay, well, if it's like this, kind of like this, then it must be this. And so those how it figures out that and how it maps that information is learned through training. So one of the good ways to practice learning about these terms is to go and read an article about machine learning. There's lots of articles. Some of them are more helpful than others. Some of them are more entertainment, but others of them are more academic. As you're going through them, it'd be helpful to start picking out these terms as you're going through it. So we found one example here. And so the title of this is Deep Learning Algorithm Does as Well as Dermatologists in Identifying Skin Cancer. And so you can read this. It was put out by Stanford University. But this could be tried with any exercise. If you know that you're teaching this session to an audience of biologists, you might pick this example. If you're doing it, teaching this to musicians, you might choose another article. But the goal of this the goal of this activity is to have the people attending your session to spend a few minutes reading the article and to try and pick out what the label, the feature, the example, the labeled examples, unlabeled examples, and the output are. It might be helpful to go back to the previous slide and show them what this is, but that's okay if they don't get it right away. When you're debriefing, that will be another opportunity for you to discuss these terms. So, for example, you could even determine some of this from just the title alone or the subject. So give them 10 minutes to go through this. And then as you're discussing this, you could ask them, okay, what do you think the label is? And they might give you some ideas. In this article, for example, the type of cancer, whether it be whether it has cancer or not malignant cancer or carcinoma, that kind of cancer is the label. So it looks at, let me go back to the article here. They use a dermoscope, which I don't think they have any pictures of it in line, but you would have this, it uses an image from the skin, and the training data labels it as a certain kind of cancer or not. And put the laser pointer on. What would the features be? Well, the features would be anything that a doctor would use to try and determine whether or not a region of the skin has cancer or not. So it could be asymmetry, irregular borders, color, those kinds of things. And those are the features that would be the information that you would input into the model. And a specific example would be an image of a skin lesion. What would the labeled examples be? That would be a biopsy confirmed. um, so, an image that was cancerous, an image of a cancerous region or non cancerous region that was labeled by a radiologist or a oncologist. Now, it's important to pause here and say that machine learning actually involves humans throughout the process. The goal of machine learning is not to get rid of humans or automate, I don't know, become so smart that machine learnings aren't needed or humans aren't needed. They are very necessary because if you have labeled examples that are not correctly labeled, like if you just try and look at it, as an untrained person, go, "Ooh, yeah, that is cancerous," or "That's just a freckle," or that, you're gonna have your model is not going to be as good as it could be. So humans are very necessary, including experts. So when this model says it does as well as dermatologists, it could be helpful to think about what does it mean to say, okay, now that a dermatologist doesn't need it can use this model to identify skin cancer, what would it change? It certainly wouldn't mean we don't need dermatologists anymore. What would it mean for the future of the dermatologist? Unlabeled examples would be, here is a new skin image of skin. What would it be? And then the output would be the prediction of cancer or not cancer, which is the goal. Um, and so those are some of the questions you can ask, but really just make it a dialogue. If you have lots of time, it'd be great to go through a second article or just put up pose a situation. So that's a great way to get them understanding the vocab rather than just telling them. Now, machine learning is more like an experiment or a scientific endeavor than an engineering endeavor. And what I mean by this is if you just try and ask a machine learning practitioner, what is the right way to build this model so that it does this? They're going to go, I have some guidance and I have some suggestions, but I couldn't tell you exactly. You're going to have to experiment. And so we've used the scientific method here. We're bringing that back if you're familiar with it in order to think of this machine learning as the process that you would experiment to try and figure this out. And so, if you're not familiar with this, scientific method is framing the problem, like, for example, what would the traffic be like tomorrow? And then making a hypothesis, which is just an educated guess. You're saying, okay, based on how the traffic was yesterday, I think tomorrow it's going to be this. Um, and so maybe you would, inform your guess based on the weather. You'd say, well, when it's not raining right now, but it's supposed to rain tomorrow, and so I can't use today's information yesterday necessarily. But the last time it was raining, it was much more busy, and so that would be your hypothesis. So I predict to be more busy. Then collecting the data, you would look at all your historical data that you could find, and also collect weather data if you think that the weather is going to make a difference. You're going to test that data or test that hypothesis and say, okay, here is here's the historical, maybe for example, you look at historical data from 2 years ago and you say, okay, let me try this year's data or last year's data on 2 years ago's data and see how it works and see if weather actually is helpful in predicting whether or not the traffic will change. And then you say, okay, is this model better than existing systems? For example, if your model is right only 50% of the time, then you might as well just flip a coin. But if you get maybe 80 or 90% accuracy, maybe this is something helpful. Maybe there would be additional information that would be even more helpful. Maybe weather is only part of the answer. And so then based on that information, you would say, okay, I should use this model because it's X% accurate. Or I should not use this model because it turns out that whether or not the uh, you know weather doesn't have any effect on it. Maybe it's the time of the day, or maybe it's whether or not there's been an accident. These are all kinds of things that maybe are more important than the weather, or maybe they're just part of the uh, puzzle. And so that's why you need to refine and repeat. Don't just say, "Oh, it didn't work. I guess I'll move on." Experiment. When you run an experiment, you have to iterate on it and say, "Okay, weather was helpful, but maybe time of the year. Maybe it's better. Maybe there's more traffic in during when time of the year when school's in session than when school's not in session." So those are all things to think about. And so this is the scientific method, and it's very easy to overlay the scientific method with machine learning because you're similarly going to frame a problem and say, okay, I want to know what traffic will be like tomorrow. That's a very clear answerable thing. I can say traffic will be this long or this um, slow or fast. And then you can try something out saying, "Oh, I'm going to use these features and this data, and I'm going to test it, and I'm going to see how it does. I'm going to measure how well it predicted, and then I'm going to make a determination on if whether or not I need to use more data, more features, different features, or a different process altogether." So here's some practice of framing a problem. Your landscaping business is hiring people for the fall season. You want to predict how many leaves will fall from a tree each day so you hire the right number of people to clean up. And so this would be an opportunity where you can choose to make this a class participation thing if you think that the entire class will participate. But if you don't think so, if you think that one or two people might hog the session, um, then feel free to break people up into a couple of break them up into pairs or groups so that they can talk through this and then talk through it together as a class. That way, everybody gets a chance to try this out. And so, for example, what could be the clear use case? Well, so again, give people time, about 10 minutes or so, to come through this and then have them debrief. Two fellow facilitators will walk through this now. So is there a clear use case in this? And so the question is, would there be a clear use case? Well, yes, you want to predict how many leaves will fall from a tree, so you hire the right number of people to clean up. So there's a very clear, if I have this data and if I have a way of predicting, I will be able to use it this way. Do I know the problem? Well, you are trying to figure out how many people to hire, and you don't know how many people you'll need on a given day. So yes, so your use case is I want to predict the number of leaves, and the problem is I want to use that information to know how many people to hire. So really, just so we're clear here, you are building a model to predict the number of leaves. But then you might be building another model on top of that to make a prediction of, if I have this many leaves, how many people should I hire? And then, do you have a lot of data? Well, you would need to get data on that. You would maybe look at trees around your neighborhood, or maybe there's some data source that you can use. And so you need to know perhaps weather. I mean, do you need to know what time of the year the trees or the leaves fall and how long do they fall for? And so these are all things that you might need to know in order to feed this information into your model. And then um, prediction. You could ask the groups to ask, would you be able from this data to make a prediction and say how many leaves are going to fall each day, or how many people should I hire? There may be differences in opinion. Some people might say, yes, absolutely, you could figure that out. Some people might say it's too hard. Some people might say it's a waste of time. It's up to, there's no right or wrong answer necessarily. And so then the question would be then, is this a well-framed problem for ML? And that is the question that could be posed. Again, people could disagree on whether or not ML would be helpful here, or whether or not you'd be able to get the data you need. But as far as machine learning goes, as far as a problem framing goes, this is a problem that you could use machine learning for. You might not be able to get the data that you need, but or you may not be able to get a clear answer, but at least you'll be able to use machine learning to test whether or not you can get that the prediction that you need. Looking at another example, a beekeeper wants to analyze pictures of their honeybees and identify their role within their colony. Okay, so this would be so again, you would give the groups the chance to go through this and think about whether or not there's a clear use case, whether or not we know the problem well enough, um, like whether or not we know what the problem is we're trying to solve, whether or not we have a lot of data, predictive power. Would this model be able to be used to make predictions? And would you be able to use it to make a decision? So, looking at this, giving them a few minutes to think about it, you can ask them to go through these again and say, okay, whether there's a clear use case, yes, they want to use, they want to be able to identify the role within the colony. And so the problem is, um, from an image, could you classify a bee as a worker bee or a queen bee or something like that? And do you have a lot of data? Well, again, you'd have to think about what kind of data you would need. You would need to get lots of different kinds of bees because there are many different, I assume there are many different kinds. You will have to get examples of all the different kinds and ways that a bee could look inside the hive and what they could be doing. You're going to need that labeled data because, again, you can't just have the data, take a bunch of pictures and have the machine figure it out. I mean, you could, but it'd be a lot more time consuming and complex. It's much better if you can have labeled data, which means that some expert has said this is a drone, this is a worker, this is a queen. Um, and so then could you use that predictive power to make decisions? Well, if you had a model, I mean, if you had this data, you had this model, you could get a new picture of a bee and have the model predict this is the queen bee. So yes, it would be able to make a decision based on that. So again, after the group has the discussion about machine learning and these different parts, you can then say, you can then have them say whether or not it'd be a good fit for machine learning. And the answer is yes, this could be a good fit for machine learning. Whether or not you could collect the data, whether or not it would be able to help is something that you can discuss. But it is definitely a potential use for machine learning. Here's another one you could use. We won't go through it, but you could definitely go through it with your students. And then finally, we want to um, have groups of people. It could be two, it could be four. Have them think through what will be, excuse me, think through an organization, make up their own use case that would benefit from a machine learning model. And so they can think through what the model would do, how it would impact the business. So this is kind of the reverse of before they were given this information, they were trying to figure out whether or not there was a clear use case, know the problem. Now it's the reverse. And we want them to come up with a use case, come up with a problem, think about the data, all those things, and use that to generate an example. And so, or a problem. And using these things, again, um, the practice of coming up with a good problem for machine learning is really important because there's a lot of things that seem like ML problems, but they are not strong enough to be ML problems. Or there's another misconception where everybody thinks, wow, machine learning is so powerful. We should use machine learning on everything. But that's also another fallacy because there's lots of things that machine learning is not a good fit for. And we want to make sure that we're not wasting effort trying to do things with machine learning that could be done with simpler means or just might not be possible with the approaches we have today. So I hope that you have lots of fun with your students using thinking through how to make a good problem for machine learning. Take care.